In this paper, we put forth design principles for visual analytics in operations contexts. We define operations as tasks that require time-sensitive attention, generate an action-oriented output, and assess risk and impact across multiple scenarios. Spacecraft command is an example of one domain characterized by operations tasks. Spacecraft are deployed to collect and relay data back to Earthbound scientists. One such spacecraft is the Mars Opportunity rover. Telecommunications operators at the NASA Jet Propulsion Laboratory manage the quantity of data Opportunity can transfer to Earth. This quantity changes daily based on numerous conditions. Among these conditions are the location of overpassing satellites, the orientation of the rover, and the topography of the Martian terrain. We can classify the work done by telecommunications experts as operations because it satisfies our three conditions. The task requires time-sensitive attention to offset a hard drive failure that wipes the data cache when the rover enters its power-saving nap mode. The task generates an action-oriented output, namely a decision about where the rover should drive, and the task requires assessment of risk and impact across multiple scenarios, since these path planning decisions must accommodate changing priorities. The existing tool used by operators was complex, time-consuming, and distributed across various interfaces. To improve this work process, we were asked to design a new tool. Our research and prototyping culminated in the design of a new system called Meridian. This tool measures the amount of data Opportunity can transmit to overpassing satellites under changing conditions. Operators begin by entering values for the time range they're interested in examining and for the rover's current location on Mars. The interface then populates with polar plots that display information about overpassing satellites the rover might connect to. The polar plots display estimates about the amount of data that can be transferred for each of the satellite overpasses at all rover orientations. If the team intends to head in a specific direction, the operator may choose to realign the plots by rotating them. The operator might then look for a heading in which the rover can be expected to transfer a large quantity of data, noted by a strong blue tone. Values in grayscale represent weaker data transfer predictions that fall below a preset threshold. Another threshold is marked on the overpass cards, signaling if an overpass falls below the recommended elevation by rendering that elevation value in red text. Clicking on the terrain icon displays the satellite's trajectory and the surrounding topography, enabling the operator to measure the risk of connecting to a low overpass and determine whether the data transfer may be disrupted by occlusion in the landscape. The operator can highlight the prospective headings they wish to examine more closely. Selected headings appear in the right-hand panel, where they can be further sorted according to the condition the operator wishes to prioritize that day, such as heading or estimated total data. Clicking on a selection opens up a detailed time series view for further analysis of the predicted amount of data that can be transferred over the duration of the overpass. When the operator has chosen a heading they intend to pursue, they can send the information to the rest of their team. We used the lessons learned from designing Meridian and looked at other visual analytics systems to come up with 7 principles that can inform the design of operations tasks. We submit the following principles to facilitate an understanding of the particular challenges of designing for these contexts and offer suggestions for prioritizing focus and framing expected trade-offs. We believe these principles contribute to a growing scholarship on designing for operations and the continued investigation of this space. Thank you.